of Technology, Allahabad. His research interests are homotopy analysis method, heat and mass transfer in porous media, nanofluidic transport, and nonlinear dynamics. He qualified for CSIR NET in 2014 and GATE in 2014 and 2015. He was the university topper in his MSc from Jivaji University, Gwalior. He has published 11 research articles and 1 book chapter so far. He attended numerous national and international conferences and workshops. He is a reviewer of international journals such as World Journal of Engineering, Asian Research Journal of Mathematics, case study in thermal engineering. So let us welcome back once again Dr. Atul. And Atul, now you can start your talk.
Thank you, sir. Thank you, ma'am. Thank you, everyone. Okay, so let me present the screen then. Yeah. Yeah, please let me know, ma'am, whether the screen is visible. The screen is visible, ma'am?
No, sir, it is taking time.
It's black.
I think I have to off my video so that the internet comes good.
Okay, blank screen is coming.
Now is it okay, ma'am?
Not yet. Still the blank screen is coming.
Actually, sir, your screen is visible. You go to your presentation actually.
Okay, okay. Is it visible now?
No, click on the presentation. Yes, yes, now it's coming. Yes.
Yeah. Now it is coming. Now it is coming.
It is coming visible. Okay.
Yeah.
Thank you so much, ma'am, for your kind words. Okay, so the topic of my today's presentation, this one is some applications of eigenvalue and eigenvector, because it's a very common field, and every engineers and mathematicians have definitely gone through this topic, eigenvalues and eigenvector. So I thought to choose this topic because it's a very important one. And we know what is eigenvalue, we know how to find the eigenvalue, we know how to find the eigenvectors, but where it is applicable, it is very important to know. So because it's a part of mathematical mathematics side, so we'll first see what are eigenvalues and eigenvectors and how we can recognize whether it's a vector is eigenvector or whether what will be the eigenvalues. So there are certain explanation I will do with the graphical representation that will help you to understand the basic concept of eigenvalues and eigenvector. So this is just an overview. Then we'll go for the application, where the application is we'll see the eigenvalue and eigenvectors applications. So the definition, this is definitions taken from the book which we have studied, that is Hoffman and Kunz. It is a scalar lambda is associated with a given linear transformation of a vector space, and having the property that there is some non-zero vector which when multiplied with a scalar lambda is equal to the vector vector obtained by letting the transformation operate on the vectors. So it's a very simple statement, but its meaning is very deep. So simple, the statement is, and this whole statement is saying in one single mathematical expression, that it is saying that A is some linear transformation and is applied over a vector x, and it is giving some eigenvalue, or you can say it is eigenvalue, a scalar multiplied by eigen vector. Sorry, this should be vector, not eigenvalue. This should be vector. Okay, so x is eigenvector and lambda is eigenvalue here. Okay, now the where we used to see the application of eigenvalues and eigenvector in designing. It used in designing, obviously. We'll see the one example here, live example of screw and bottle and all. That will help you to understand how uh, the eigenvalues are applicable. Then it is also help in Fibonacci sequence. It's a very you will very fascinate to know this, how eigenvalue is there in Fibonacci sequence. Then it is also tells us how much deer is safe and how much deer is uh, at risk from the lion. So one application we'll see in here also, and there is certain more application we'll see like in mass on the spring, and there are further examples we'll see. These are the basic examples which we see in our daily life, but there is one more research related equation is also there, eigenvalue problem, that we also will solve that one. So suppose this is x and y axis, and there is a linear transformation A, which is 1 minus 2 minus 5 and 4. It's a quite simple 2 cross 2 matrix I have taken as a linear transformation, and I'm going to apply this transformation over a vector, and vector is this x. Vector is 2 minus 5. Let me apply this vector A over this matrix A, or linear transformation A, over this vector x. I think my daughter is somewhat just wait a minute, huh? Sorry for the interruption.
It's all right. It's all right. No problem.
So I'm going to apply this transformation A over this vector A, x, and let's see how it will yield. Suppose this vector x is, I have taken 2 minus 5. I'm going to plot this 2 minus 5 point in this direction. Okay, from the origin. This is good. Now this is your this is our x, and I'm going to apply the transformation A over x. The transformation can be just can be like a multiplied by x. So just a is multiplied with x, or we can say transformation A is applied over x, and I'm getting the result 12 minus 30. Now if I plot this 12 minus 30 in the x and y, this xy plane, I'll have it will be somewhat here. And let's plot the line. Now we got this point at 12 minus 30. Previously, this vector is at 2 minus 5. The vector was 2 minus 5. And now after applying the transformation, it shifted to 12 minus 30. Okay. So I can, what I can see here, that minus 2 minus 5 is scaled sometimes. If you notice, it is scaled 6 times, isn't it? 2 minus 5 is scaled 6 times to reach out to 12 minus 30. So it means this ax is 6 times of this x. This ax is 6 times of this x. If you relate this with the definition, ax equal to lambda x, the whole story is clear. Means the lambda is 6 here, which is our eigenvalue, and this x is eigenvector. So it's a quite simple thing, that here lambda value, eigenvalue is 6, and the definition is very much clear that if x is an eigenvector, this scaling factor, that 6 means here it is a lambda, is called eigenvalue of the transformation. Okay, so next question we can have, can all vectors be eigenvectors? Because randomly I have chosen this vector 2 minus 5, and I found that this is eigenvector because it is satisfying the condition ax equal to lambda x, or 6 times of x. So can all vector be eigenvectors? So suppose I am again considering the same plane, xy plane, and this time I am considering a vector 1 2 instead of 2 minus 5, which I have taken in the previously. Now let's check out. Again, I will try to implement or apply the transformation A over this vector x. And now this time I am getting minus 3 and 3. If I locate this point 1, 2 on the graph, it will be here, somewhat here. But after the transformation, this point reach out at minus 3, 3. So this time it is not scaled. You cannot express ax equal to some lambda times of x because this is not scaled x. This transformation didn't scale x. This transformation has rotated x. Yeah, it is scaled, but rotation as well. So in that case, can I have that lambda? No, absolutely no, because we cannot have ax equal to lambda x form here. So this vector which I have considered x equal to 1 2 is not an eigenvector corresponding to this transformation A. So it is quite, and our answer is, what is our answer then? The answer is all vectors cannot be eigenvector of a transformation. There would be a certain or fixed eigenvectors. Eigenvectors can be infinite, that we will see. And now the next question, can eigenvalues be negative? Why I am telling all this? Because this will be help us in understanding the physical concepts. Can eigenvalues be negative? Eigenvalue negative हो सकती है क्या? So let's see this transformation. Again, the same transformation I have taken, because with the same transformation it is easier to understand the concept. So this time I have taken a vector 1 1, okay, and I have applied this transformation A over 1 1, and I get minus 1 1. So previously it was 1 1, and after applying the transformation it becomes minus 1 1. Means the direction is just opposite to that. But yeah, this all are in a one line. It is scaled, but in a negative way. So the vector goes down in negative direction. But yes, I have one lambda value, one value for which we can have the equation ax equal to lambda x, which is ax equal to minus 1 times of x. That means this lambda is minus 1. So yes, there is a possibility of having negative eigenvalue. So let's there is a cross check with the Mathematica program. You can we can have this one. I think it is not opened here. Let me open this one to get the clear view. I hope, is it visible? Yes.
Yes, it is visible.
Now we can see the first one. It is better to make it down to understand. Yeah, so 1 minus 2 5 minus 5 4 is the matrix, and its eigenvalues is obviously here it is given 6 and minus 1. So starting at the starting slide, we have seen that 6 is one of the eigenvalue, and another eigenvalue I am getting the negative one is minus 1, and corresponding eigenvectors are this one, minus 2 and 5, which I have taken in the first slide, and in the third slide I am taking 1 1 intentionally, just to understand the concept. Okay, so now there is a simple one question in this. This is the cylindrical uh, surface. So I'm taking one x1 x1 axis is one direction, and x2 is this vector. So can I have a question? Which one is will be the eigenvector out of this? Which one can be the eigenvector? It's a quite simple thing. If I apply the rotation, which one will be eigenvector?
X2.
Yes, correct. I was expecting this. So if I rotate, x1 will definitely rotate. This vector will rotate in some angle. It will not scale. It will rotate. But yeah, x2. Definitely, x2 will scaled as in the same direction. Now, if I take one simple example, I think hope you all can see me. This is a bottle. This is a live example, okay? So this is a bottle, and I'm putting my finger like a vector over this, and I'm rotating this one. And if I rotate slowly, I will reach to the end, isn't it? Can you say this? You can try. You can also try by just open the cap of the bottle, and there will be some patterns, circular pattern. But their direction, you see, you focus on the direction. This direction is not the circular. The direction is just rotational, isn't it? I think I hope you all have some bottle with you.
Like
Yes.
little bit spherical type का
Yeah,
थोड़ा
yeah.
orbital type.
Orbital type. But when I keep my hand in a orbital direction, slowly it will reach to the from above. It will reach to end. So what I am doing here, I am applying the eigenvector. This hand, this finger is not. Finger is eigenvector, and I'm rotating. I'm reaching to the end. So this application is actually applied in many. This actually you see here also. I forgot to say this one. Inside also, the same pattern is there, so that it becomes slowly it becomes law where the vector end. So this is one physical example of this. Okay, so this same thing will be applied here also. So yeah, you are right, ma'am. This x2 is definitely will be eigenvector here, because it is not rotated but scaled. Okay, now let's come to Fibonacci sequence. We all know this sequence: 0 1, and then 0 plus 1, that will be 1, 1 plus 1, that is 2, 2 plus 1, that is 3, 3 plus 2, this is 5, and so on. So how we can have the eigenvalue here? Can we think about this? So yes, there is a chance. If I ask simple question, what will be the next number? What will be next to this number 832040? 832040 also, if it is asking, so it's quite simple that it will be also a term of the Fibonacci sequence. So what will be the next number? So in that case, we can apply the eigenvalue concept here. Let's have this one as a sequence, it's a sequence, so it can be A naught or T naught, term T naught, term T1, term T2, and term T4, and so on. So let's see, in general, we know this is Fibonacci sequence, so we'll have Tn, it's a recursive relation. Tn is equal to 2n minus 1 plus Tn minus 2. So can I write like this? Tn is, if I Tn is Tn minus 1, and then I have made one relation transformation 1 1 0 1. If you then I multiply it with T minus 1, Tn minus 1, T minus 2. If I simply multiply, and if I see, you will have the above equation. Tn is equal to Tn minus 1 plus Tn minus 2, and then lower equation will be Tn minus 1 equal to Tn minus 1, same. So with the help of these two equations, we have made this transformation. So here one you got this one transformation matrix, that is 1 1 0 1. So I'm going to find the eigenvalue of this. So eigenvalue here also you can means it's just a cross check, because if Tn is 13, so 13 will be the sum of, definitely sum of 8 and 5. So it will yield the same thing. So it is just just for cross check. 8 is equal to 8. Okay. So what is the next number to this? For this we will find the eigenvalue of this number, this matrix 1101. So obviously the eigenvalue for this matrix is 1.618. Now we have obtained the eigenvalue. This eigenvalue 1.618, it is not just a number. It is not just a number. This actually number is called the ratio. And what ratio? Golden ratio. So this is a special one. This number is special. This eigenvalue is special because it works for the longer run. Now you see how. If I like to have the number next to 13, and from here above we can see the next number is 21. The number next to 13, you just multiply this 13 with 1.618, this golden ratio. You will have the next number 21.034, which is nearly equal to 21. Let's see another example. If I have the number next to 21, so I will just multiply this 21 with golden ratio 1.618. It will be nearly equal to 34, which is our next number. Similarly, if I ask the same question, which will be the next to 832040, so nothing to do, just multiply with this golden ratio to get the next number, which will be 1346240.72. It is just one step away from a multiplication. Just you multiply 1.618 with this number, we'll get this. So this eigenvalue concept is very important in this case. Now, if you think that yes, Fibonacci series will start from 0, no. This golden ratio will work for all the numbers, which it can be start from any, like 5 plus 13, that will be 18, 13 plus 18, that will be 31, and so on. Similarly, it can start from 7, 12, 7 plus 12, 19, 19 plus 14. It will yield the same result. The same concept I will use, the same result I will get. And one more thing, this will work as a this will run if I plot this the points, the two consecutive point, I will have the curve like this, you can see. And for a longer run, you will see that it is going in a one direction that will perform as a vector. You can fit a curve line on this points. So from 2 or 3 points we have seen here. What is eigenvector? It will go directly to the scaling vector. Scaling factor is nothing but eigenvalues. And one more thing we have seen here, that it will eigenvalues and eigenvector reveals the long term performance. Okay, so let's see the more application related to eigenvalues and eigenvector. In terms of designing, I told you this will see, like you see here also, in it helps in drilling uh, machines also. I think you all have seen the drilling machine with which we fix our screw and all on the wall. So you can see the same pattern is there, same spherical, what you are saying, helix type, uh, the curves are there, and the vectors, you can easily say which one will be the vector which is given in the orange color. Similarly, in design application, how is it used? Obviously it is also a design, and this in a drive wheel, because there is a shaft. When we apply a brake, how this uh, the wheels get stopped. The reason is, when we apply brake, there is a certain uh, force is applied to restrict the motion, and that you can also see the spherical, you can see the CV shaft here, the drive shaft, with which the our vehicles get stopped. So when we apply the brake, this the things which you see in the spherical types, that helps in restricting the motion of the wheel. So this is just one application. Now let's see how in real life, in means land air population, how it works. Suppose land population is L and deer population is D. So suppose that the ratio of that rate of change of uh, birth of deer is proportional to the four times of deer minus present lion population, because lion, if lion is more, definitely the deer will be less. It's a just vice versa thing. So, and the lion present, the rate of change of lion is proportional to the present population of the lion. If there is a such problem, how eigenvalue and eigenvector helps here in understanding the concept. So this, I think it is a very simple differential equation. You can easily solve it, but we need the concept of eigenvalue and eigenvector here. So I can express this transformation in this form: d dash l dash, d dash represent dd by dt, and l dash represent dl by dt. Then you will have the transformation like this. So we again have a one matrix. Let's solve this matrix and find the eigenvalues and eigenvectors. So definitely it is a upper triangular matrix. So its eigenvalue is 1 and 4. Obviously, we know. Then what will be the eigenvector, and how that eigenvector helps in predicting the nature of existence of deer or lion. So let's see. Let lambda eigenvalue is 1. So after substituting ax in a minus lambda a multiplied by x equal to 0, in lambda equal to 1, and then we find the value of x, that is 1 and 3. It's a usual way. So it is directly I have written for after finding, and we can have used the mathematic or MATLAB for finding the eigenvalues, eigenvector very easily. So when I applied this on the so you can see one red line graph curve. This is actually eigenvector. This is 1 3, then 2 6, then 3 9. Similarly, -1 -3, -2 -6, -3 -9. From that, this line is drawn, and this is the eigenvector. And there are multiple infinite points on this line. So there, with the help of this, we have plotted this one. So now here, this you can search on the net also. This is called phase plane graph. So you can draw it easily. The y-axis is here corresponds to lion, and the x-axis corresponds to deer. So this is the eigenvector. Okay, so this is the reason where deer is safe. This is the reason where deer is clearly safe, and just below the red line, just below the eigenvector. Above the eigenvector, the deers are very danger, in danger. Okay, so suppose if I increase the number of, if I increase the lion population, or you can say if I decrease the deer population. So in that case, what will happen? Just one uh, thing happen here. It is 2. I have changed the 2 instead of 4. Now you see the same step I'll follow to get this curve. Now you see the number of, if the number of lions is increasing or the number of deer is less, so there is a very dangerous situation for the deer to survive. So in that case also, because we have taken two eigenvalues and eigenvectors, so similarly it is taken. So there is one more example. There are many multiple examples is there. Here I have taken some of the most common examples in eigenvalues and eigenvector. Suppose we are searching for something on the net. It is Google's page rank. It is, you can search on the net also. You will find this one. It is a Google's page rank. Which page will occur? It's a quite simple. When we see the when we search on YouTube, so there is certain recommendation used to come on the YouTube while searching. You can see any video, just below that there will be a certain recommendations. How these recommendations comes, and why only those recommendation comes under those uh, video, under the video which you are seeing. Why they are just popping up, just uh, in front of your eyes? Why? What is the reason? The reason is, suppose, because it's a totally complete strategy. Okay, so suppose page 1, there is a page 1. Okay, it is going towards 4. Its simple means is that page 1 likes page 2, page 6, and page 4, page 5. These 4 pages is liked by page 1 in a simple sentence. Page 2, or a person, you can sorry to say page, but you can place here person also. The person who likes page 2, page 2 means a certain site, suppose, because you are following also one site. So one site is following other site, so they like other one another. So you can analog with this. So there are many multiple things you can here say. So we place, so in that case, because there will be a total probability of 1, so we'll divide our probability, total probability 1, in 4 different parts for page 1, because page 1 is going towards page 2, page 6, page 4, and page 5. Similarly, page 2 liking page 4 only, and then page 3 likes only page 5. That's it. Page 6 likes only page 5, because it is going towards page 5, and page 4 likes page 5 as well as, and nothing. Okay, similarly other. So in that case, what will be the eigenvalue and eigenvector, how it will be helpful? So we'll make definitely one uh, matrix for this. Here you see there are 6 cross 6 matrix, because you will have 6 pages. If we can have the multiple pages also instead of 6. Okay, so it's just an example is taken here. So that's why here you see the first column corresponds to the page 1 is liking which page. So page 1 is liking page 2, that's why here 1 by 4, 1 by 4, because total 4 pages he likes. 2, 6, 5, and 4. So instead of 2, 6, 5, and 4, there is 1 by 4, is means total 1 by 4, 1 by 4, and 1 by 4, and 1 by 4. Completely, you will, if you will add, you will have 1. Similarly, page 2 likes page 3 and page 4. Okay, so you'll have this one. Similarly, third one, fourth one, and fifth one, and sixth one. Now there is a MATLAB code just applied here to get the eigenvalues, because it's very difficult to find eigenvalue using hand. Okay, and there will be a complex eigenvalues also here. So it is preferred to use the mathematical tools and softwares. So MATLAB code is used here. Uh, so to get eigenvalues is here. Two eigenvalues are definitely zero here, and one eigenvalue is one, and the second eigenvalue is negative. Negative and complex eigenvalues are not related to this problem, because if you are liking something, then that it will consider as a positive quantity. If you are not liking, it will directly zero. Okay, so there is no concept of negativity here. So it lambda is equal to eigenvalue only, which is suitable to our case is lambda equal to 1 only. So if I have the lambda equal to eigenvalue 1, and I will solve the 6 system of equation or 5 system of equation, I'll have this eigenvector. From this eigenvector, I can see which uh, element is more, that is most liked page from the 6 pages. So if we see the 8 is more than other element of this vector. It means the fifth page is that page which is liked by many pages. So definitely if you search something, the page 5 will come first. Okay, so this is a basic, very basic and very important application of eigenvalue and eigenvector here. Okay, so this is very important one. And now let's see one application, one research problem. I think many of us have solved this Gelfand equation and familiar with this Gelfand equation. There are different forms also of this, but one of the form which is suited to my uh, my method, like sorry, means HEM method, because homotopy analysis method I use here. So this is most suited equation which is solved by HEM. So that's why I considered here is here. Here you see lambda is nothing but eigenvalue. Okay, and the u what I will get here, that will be eigenvector. And so this is quite a simple, it is not simple, but eigenvalue problem. Okay, so use that his here eigenfunction. Make one point that all eigenvectors are not eigenfunctions, but all functions are eigenfunctions, eigenvectors. Okay, so we need to find this u as well as this lambda. So for finding the, because there are many eigenfunctions means there will be many eigenvectors, but out of many eigenvectors, if I wish to take only one eigenvector, so for that I put another one more condition, u of 1 is equal to a. Okay, this a is taken as 3 in the equation, but I think it is not mentioned here. So Gelfand equation is this one, and it is solved by, as I told, it is solved by homotopy analysis method. The eigenvalue which I obtained here is 1.90921, and the eigenfunction which I am getting is this one. It is third iteration eigenfunction. Similarly, we can have the fourth, fifth, and sixth iteration, which will have the better eigenfunction. But this is the more accurate eigenfunction. So this is the eigenfunction, means eigenvector corresponding to this eigenvalue, and this command is applied here to get the eigenvalue here. This curve, how this curve is works, because it's also part of research field. So eigenvalue problems are used in many fields, in different multiple fields. So I think it is up to now. This is now there will be certain things we need to uh, follow. We should avoid this, and we should adopt this. If we are facing any problem, just we need to consult doctors. Thank you so much, guys, for listening me. Thank you so much.
Nice presentation, Atul.
Thank you so much, ma'am.
But unfortunately, I could not listen to you from the from beginning to end because of some disturbances here in the office. Anyway, the recording is there. I will go through it again. Mm.
Sure, ma'am. Sure. No
Okay.
issue, ma'am. No issue.
Yeah, yeah. Any questions?
No, ma'am. Not yet.
यार इतना खराब भी नहीं था यार
No, sir, it was.
बहुत ही अच्छा था अतुल, don't mind.
एप्लीकेशन पॉइंट ऑफ व्यू था चलो
बहुत
ठीक
ही अच्छा था because I told you na I will go through it again. It
ओके
was very
ओके
interesting actually.
थैंक यू सो मच मैम ठीक है कोई दिक्कत नहीं
Very good side of eigenvalues and eigenvector you said. Particularly, I could not listen to you regarding the lion deer problem. So
Okay,
that's
okay.
why I am thinking of going through it again. And only I joined at the last point when you were going for that page searching. There only I could join because some people came to me. Anyway,
Thank you so much.
recording is there, no problem. So very general thing with a very beautiful application part you mentioned over here.
Mhm.
So very nice presentation. I actually I've heard of this thing newly because I've never explored that area, but this is new. That lion deer problem and this page searching, etc. Very new side of eigenvalues. Its application side.
Yes ma'am, yes ma'am.
So I think everybody must have enjoyed this session. If they, and any question?
A bit only.
Abhijit?
Ma'am, actually, in place of Abhijit sir, I am doing the vote of
Yeah,
thanks
no.
today.
Yeah. I know it. But Abhijit is there. That's why I just asked.
No, ma'am, actually, I logged in from his account.
Oh, acha.
Actually ma'am, I was
Okay.
joined that time but no one has allowed me, so that's why I think ma'am has joined as
Yeah.
a
नहीं सर एक्चुअली
Come.
हुआ क्या ना लाइक रिकॉर्डिंग का परमिशन उसी के पास होता है हु
हाँ
हैज मेड
वही
द लिंक
Acha.
सो आई
Right.
जॉइंड द लिंक थ्रू माय अकाउंट बट आई वाज अनेबल टू रिकॉर्ड द वीडियो
अच्छा
And,
अच्छा
okay,
सो
Priyanka, let's formally thank Atul. Then you stop recording, and then
यस
we
मैम
can continue talking with Atul. No problem. Okay.
ओके मैम
So
ओके मैम
thank you so much,
thank you
Dr.
ma'am.
Atul. Really, thank you so much.
Okay
You are
ma'am.
our sincere colleague and friend,
मैम मेरी कभी
ex-colleague.
भी जरूरत पड़े आई एम रेडी मैं
Yeah. So
कभी
thank
भी
you so much for this nice presentation on eigenvalues and eigenvectors. Thank you so much. I wish you all the best for your future ahead.
ठीक है थैंक यू
Manju
मैम
has written. It was a nice presentation. Manju has written. Okay.
मंजू मैम
So
इज
thank
ऑलवेज
you.
सपोर्टिव
Yeah. She is always supportive and very sincere like you.
यस
Very active and very prompt.
वेरी गुड
Yeah.
यस
Yeah. Priyanka, you can stop recording now.
ओके
ओके मैम मैम व्हाट अबाउट वोट ऑफ थैंक्स
Uh, okay. I, I thank him. You offer from your side, vote of thanks. Okay.
Yeah, okay. So, thank you, Atul sir. Yeah, thank you, ma'am. So, at the end of the 21st Siksha Anusandhan weekly academic lecture, I shall take the liberty of proposing the vote of thanks. So, we thank the speaker, Dr. Atul Kumar Ray, whose talk has undoubtedly enriched our knowledge on possible mathematical applications of eigenvalues and eigenvectors. Our thanks are due to the colleagues, research scholars, and students who has joined as the audience. And our big thanks to go to Dr. Manoj Ranjan Nayak, the Honorable President of Siksha Anusandhan deemed to be University, who has always been a source of inspiration to all of us. I extend our thanks to Professor Manjula Das, the head of Center for Data Science, for the necessary supports, and especially Dr. Amit Kumar for helping us to connect with Dr. Atul Ray. In the last, I, on the behalf of the Center for Data Science, uh, extend our heartfelt thanks to everyone. Thank you, sir. Thank you, ma'am.
Thank you. Thank you. Thank you.
Yeah.
Stop recording
Yeah,
so
ma'am.
that